We have two concentric semicircles, both resting on the same flat bottom line, and both sharing the exact same center, point O. The smaller semicircle sits inside the larger one, and the curved region between them is shaded green. Now, here's the interesting part. We're given just one measurement. A horizontal chord, AB, connects 2 points on the outer semicircle, and this chord just touches the top of the inner semicircle at exactly 1 point, point P. The entire chord AB is 8 units long. Our job is to find the exact area of the green shaded region. And notice something important. We aren't given the radius of either semicircle. At first, that might seem like a problem, but surprisingly, we don't need either radius individually. Let's see why. First, let's write an expression for the shaded area. Call the radius of the large semicircle capital R, and call the radius of the smaller semicircle lowercase r. The green area is simply the area of the large semicircle minus the area of the small semicircle. Since the area of a semicircle is pi times the radius squared divided by 2, our shaded area is pi times capital R squared divided by 2 minus pi times lowercase r squared divided by 2. Factor out pi divided by 2, and we get pi divided by 2 multiplied by the quantity capital R squared minus lowercase r squared. So everything comes down to finding just one thing, capital R squared minus lowercase r squared. Now, look at point P. Let's connect the center O directly to P. Because P lies on the inner semicircle, OP is the smaller radius, lowercase r. And because AB is tangent to the inner semicircle at P, the radius OP must meet the chord at a right angle. There's another useful fact here. Since OP is perpendicular to AB, and the perpendicular from the center of a circle to a chord bisects that chord, point P is the midpoint of AB. The full chord is 8 units long, so PB is exactly 4 units. Now, connect O to B. Since B lies on the outer semicircle, OB is the large radius, capital R. We now have a right triangle, OPB. Its vertical leg is lowercase r, its horizontal leg is 4, and its hypotenuse is capital R. So now Pythagoras gives us exactly what we need. Lowercase r squared plus 4 squared equals capital R squared. 4 squared is 16, therefore, lowercase r squared plus 16 equals capital R squared. Subtract lowercase r squared from both sides, and we get the key result. Capital R squared minus lowercase r squared equals 16. And that's the entire trick. We never needed to find either radius. We only needed the difference of their squares, and the geometry gave us that difference directly. Now substitute 16 into our area formula. The green area equals pi divided by 2 multiplied by 16. 16 divided by 2 is 8. So the exact area of the green shaded region is 8 pi square units. And as a decimal, that's approximately 25.13 square units. A beautiful little geometry puzzle where one simple chord length gives us the exact area without ever knowing either radius. If you enjoyed this problem, like the video, subscribe for more daily math challenges, and I'll see you in the next one.